Right code. Okay. All right. Where do we stop? Gate source drain. Metal 1. Okay. Okay, can you see the slides? All right. Let's continue at metal 1. We started at metal 1 yesterday. All right. So metal 1, yeah, right. So we have got metal 1 now. And we've learned yesterday that metal 1 consists of a couple of layers in the layer, right? So for example, in this particular case, we have tinitride, we have aluminum copper, we have tinitride again, and we have titanium at the bottom forming a single layer. We call metal 1. So what is next? So this is the starting of backend processing, right? So when we hit metal, when we hit VR, when we hit metal plug and everything, so that means you're already in the backend of the wafer fabrication process. So we next pattern the metal 1. So we want to open certain areas and close certain areas. So let's see what do we have next. So we pattern the resist. So we etch metal 1 using RIE, fluorine-based chemistry. So let me get my pen. So we use RIE as usual, as what we did yesterday as well. So we use RIE, okay, reactive ion etch, anisotropic in nature, using fluorine gas, chlorine gas in this case. Multiple etch steps are required due to multiple different metal layers. So it looks like it's just a single layer, but you need to actually do multiple etching steps due to the presence of multiple metal layers, like what we see on this page: 1, 2, 3, 4. 1, 2, 3, 4, right? So 4 layers. So therefore, you need to have like 4 sub steps for you to etch 4 different layers in the metal 1. Okay. Next, you strip the resist, because resist is not going to be there forever. It's just a medium for you to do patterning. It's not supposed to stay in the device permanently, right? So you've now patterned your metal 1. Okay, so you've got pattern metal 1. Next, we deposit IMD. So the word here is deposit. So undoped silicon dioxide. Undoped silicon dioxide is deposited using successive CVD process, and etches to achieve filling between metal lines. Approximate thickness is about 1 micron, more or less. Okay, so micron. So the role is to insulate, electrically insulate metal layers from one another. So now we're talking about metal 1 to metal 2. Okay, metal 1 and metal 2, and we're going to see similar things on 2 to 3, 3 to 4, until the top metal. So we then polish our IMD, right, using CMP process to achieve a flat surface of the IMD layer. If not, we're going to have bumps on the surface. So bumps cannot be tolerated, okay, from the underlying topography. So it's going to cause, when you have bumps, it's going to cause a problem for the subsequent lithography step and degrade metal step coverage as well. So last time in lithography, we have learned that to be able to do a good patterning, you need to make sure that your surface is super clean and super smooth, right? Then only you can focus your exposure well. So we've discussed about DOF last time, right? So we've discussed about a couple of issues concerning lithography process as well. So you need to make sure that you have the right focus. So therefore, bumps shouldn't be there in the first place for you to do patterning. Then you CED again to pattern VR, to define the VR for the next connection. Right, VRs are the contact openings in the IMD layers, enabling electrical access between metal layers. So metal to metal is going to be connected by VR, right? Metal, if you can imagine metal like this, and the other metal is like that. So the perpendicular part is VR. Metal, VR, metal, VR, metal, VR, right? Repeatedly, metal to metal is connected by VR at certain locations on the wafers, right? Enabling access. Next, we etch the IMD RIE process using fluorine chemistry to achieve vertical sidewall, so anisotropic in nature. So you remove the IMD down to the metal one. So if, for example, kalau you run the etching process RIE ini, you run the etching, then you don't etch. For example, you accidentally you don't etch IMD1 completely. So what's going to happen? So you're going to have some remaining IMD on metal 1. Kalau you etch sampai sini je, so the remaining down here is IMD. So you have IMD1 residue, for example. This is considered defects. So what would happen? What do you think would happen if you etch IMD1 but incomplete? Apa akan jadi? What do you think will happen? Will the metal 1 and metal 2 be connected? Yes or no? Not connected, right? So why not connected? What is IMD? What is IMD? You think IMD ini? So can anyone search what is IMD? Cuba Google search what is IMD. Siapa yang dah jumpa, letak kat jawapan dekat chat box. You search first for like 15 seconds. Anyone? Anyone found anything? What is IMD? Kau jumpa dah, search. Intermetal dielectric. So is a dielectric or is a metal? So it's a dielectric, right? So it's a dielectric. So it's supposed to insulate. Metal 1 to metal 2, 2 to 3. So between metal layers. So it is a dielectric. So if it's not etched completely, you will not get contacts between metal 1 and metal 2 because you have dielectric sitting on the metal, okay, blocking the metal from being connected, okay. So that's why you need to make sure that your IMD is completely etched. So normally when you finish every single process that you do here, you need to do visual inspection in the fab. So by Leica microscope, you need to put the wafers after the etching process to be inspected, then you can see whether you still have IMD residue or defects or particles. Then only you proceed with the next step, okay. So it has to be ended with visual inspection process after every single processing. So it's embedded in the process flow as what I've discussed last time, yesterday, right? I mentioned about SP02 spec. If you talk about Silterra, so you can see the visual inspection step in the process spec as well. Then we strip off the resist. Okay, we strip off the resist because it's not supposed to be there forever. Okay, resist strip. Then okay, tungsten. we do so we deposit tungsten nitride or tinitride and tungsten, same as for the first interconnect layer. So you've seen that between our device, the front end and the back end, and the metal one. We've seen yesterday that we've done a tungsten plug deposition, so we're just going to repeat the very same deposition layer for this particular step, right? So we deposit tungsten, so then we polish tungsten by CMP. So the moment you have deposited tungsten, you already have the tungsten via plug. So you connect. So you open the hole, you open the via for tungsten to be deposited, right? So the moment you have tungsten deposited in the via, so you're gonna have connection between your metal layers, right? So you make hole, you deposit tungsten, you CMP tungsten, and then you prepare the next layer. What's next? Metal 2. Subsequent metal stack to be similar like metal 1, but tend to increase the thickness in width as they runs longer and they carry more current. So the moment you go for higher metal stack, it's going to carry more and more currents out of the device. So therefore the thickness is usually thicker than the previous layer. Okay. So they carry more current. So you have your metal tooth here. Okay. Next, we pattern again, just like what we did on metal 1. So pattern 2, pattern metal 2 interconnects. Okay, then we remove, we etch the metal. You pattern metal, then you etch metal using RIE. Then you strip off the resist because it's not supposed to be there. So you now have two metal layers completed, right? 2 metal layers completed. So what's next? You deposit passivation layer, for example, silicon oxide, silicon nitride, oxynitride, polyimide, and others. Is supposed to protect the completed circuit from scratches, contamination, and moisture. So that is the rule of a passivation layer. So this is normally done by PECVD. Normally done by PECVD. So this is just a simple device structure. So you have like 2 metal layers and then wrap up or encapsulated by passivation layer and pretty much done. So the final step is you remove, so you can see here, you pattern the passivation layer. Polyimide passivation is photo definable. For example, if you talk about polyimide, other layers require a patterning resist layer followed by etch step in order to open a space for the bond pads. So bond pad ni dia punya connection dekat chip yang you nampak dekat chip packaging tu. So bond pad openings allow electrical access to the chip. So nanti you akan ada pad kat sini connecting wire lah basically ya, wire. Nanti kita try tengok how does a bond pad look like, right? So bila sampai kat sini it's already at the back end punya technology ya. So normally the process step in wafer fabrication only covers up to this step. Bond pad ni semua is not done in wafer fab, it's done in the back end, right? You can check back end semiconductor companies, then they do they do all the bond pad interconnection and stuff, right? So next, done. So can you recall? So bond pad done. So in reality, okay, let me tell you a few things. In reality, we have metal 5, metal 6, then top metal. So if, for example, if you talk about more metal layers like metal 5, metal 6, so what you need to do is you have to repeat the very same process pretty much with perhaps different thickness of the layers, different opening of the VR and stuff like that. But pretty much you're going to repeat the insulation layer like IMD. Then you're going to have like, for example, if you have metal 3, so sekarang kita start at metal 2. If you need to have metal 3, then you need to have IMD 2. After metal 2, you're going to have IMD 2. Then you're going to open the VR, you're going to deposit tungsten plug, you're going to CMP the plug. Then you're going to deposit metal layer, your metal 3 layer, you're going to pattern the layer. and then see whether you need to finish the process at metal 3 or you still have to have another metal layers. So if you have to go for another metal layers, then you need to repeat pretty much the same processes to be able to get your metal pattern. Then next, metal 3, metal 4, metal 5, metal 6, top metal, passivation, edge bond pad, opening, then leave it done. So that's why it takes longer and longer, because you have to repeat your interconnection layer, right? So the layers on the back end are called interconnects. So your metal and VR and plugs, these are all interconnection layers to be able to extract the current from the device and send out the signal, whatever. Okay, so if you work in a fab normally, for example, if you have two metal layers, or maybe too simple. If you have, for example, maybe 6 metal layers, then how do you know your device is working or not? Any idea? How do you know your device is working or not? Can you check after completing the process, or can you check anywhere intermediate? Any idea? No idea. Kalau you punya metal layers are not so many, maksudnya kalau you ada like 2 metal layers, perhaps you can just complete the process and test the functionality of the device. But if you have like 6 or 7 metal layers, and that's gonna take very long for the device to finish, then only if you want to test the functionality of the device after completing the process, then you would have to wait for like 2 to 3 months. Then only you can know whether your device is okay or not. So that's why normally when I was in Solterra last time, the tests are done at two steps. The first one is, of course, when the device is completed. For example, if you have 6 metal layers, then you finish everything, then you will test the device functionality. So then you will know the yield. Let me write it down here. Yield. Dia punya produk tu okay ke tak? So normally you have a minimum target of perhaps, I don't know, 98% or 99% or 99.5%, depending on the devices and customers' requirement. So the moment the wafer fab commits to deliver search yield, search, for example, if you run a fab, then you commit to always deliver 99.5% of the yield in the chips, then you have to deliver 99.5% all the time. So that means the functionality is 99.5%, and this can be tested when the device is completed, or last time we did at metal 1. So the moment metal 1 is done, then we can do a test already. We call it e-test, electrical test. Ini untuk chip Kalau you join Solterra ke Infineon, I'm not sure. I'm not sure whether they call it by the same name or not, but in Solterra we call it e-test. Means electrical test. So there's even a department called e-test. They can test functionality of the chip at metal 1, so they can probe and test and see whether it's working or not. So that will roughly tell you that your device is working with certain specifications, and then the device is going to be retested when it's completed, say at metal 6. After metal 6, it's going to be tested again, and following, it has to follow certain specification as well. So then you can tell whether or not your device is okay. Usually when you run your test at metal 1, you wouldn't get the whole story yet, because there are still a couple of layers to go. You're gonna have IMD plug via metal 2, and then IMD to via plug CMP. So you're gonna have a lot more processes to go through, which could contribute to any abnormality in the device. So the abnormalities can be defects, can be DICD, FICD, can be bumps, can be Particles can be many different things that is inspected by the department. We call it inline monitoring, ILM. Dalam istilah we call it ILM kan. Ini department yang dia akan inspect defects dalam device. Inline monitoring, ILM. That's a department for that. So kerja dia check defect for every process step. So if you are an ILM engineer, then you'll probably be assigned as ILM for front end, ILM for back end for a range of different devices. So you can tengoklah all the defects, all the kalau for example if you look at the front end of device A, then you're going to be looking at the defects for implantation, the defects for spacer nitride, for polygate, for gate ops, for silicide. So if you are a defect engineer for the back end, so you're going to be looking at metal 1 defect, IMD, BPSG, spacer, tungsten defect, VR, DICD, FICD, passivation defects, etching defects, and stuff like that, right? So we now dah nampak gambaran kan? So done. So let's review. So normally dalam kelas I will ask students to come to the front and name the layers. But sekarang tak boleh, I tak boleh apa ni suruh you label lah, because we are now virtual mode. So if you want to test whether you understand the layers, at least for this simple device, try to label on the layers that you have on this screen, on this slide, and try to tell yourself, how do you prepare this particular layer? What sort of thickness? What is the process required? How much is the dimension, for example? And then if you dope, then how much is doping level? Do you go for shallow? Do you go for deep? Do you go for high energy? Do you go for low energy implant? Where do you need diffusion? How thick is the tungsten plug? How thick is the silicide? What's the role for silicide? What does the passivation layer do? How many metals do you need? What is the role of IMD1, BPSG? How do you prepare BPSG? So on, right? So on. So you try to explain to yourself to make sure that you understand the integration of at least this simple device. If you can tell yourself the role and the layers and the function and the process and the specs and stuff, then that means you understand the basics of process integration. So the integration, the complexity of the integration varies from device to device, product to product, process to process, companies to companies. So if you talk about CMOS with like 5-6 metal layers, and of course it's going to be a lot more complicated. If you talk about some other devices like, for example, power devices, or what else? Silicon photonics, which can also be fabricated in the wafer fab. So the complication of the process really varies from device to device. So you can tell that by looking into the process specification, process spec. We call it process spec. We hardly say specifications in the fab. We normally say specs. Process specifications or process specs. If you talk about Silterra, then it's called SP02 document, XXXX. So you're gonna have like SP02 for device A, SP02 for device B, device C, device Z, device X, something like that, right? So you can tell by the number of steps that you need to go through to be able to complete the process. So the more the steps you have, the more complicated the device will be. The lesser steps you have, the more simpler the device is. Okay. Done with process integration. So do you have any questions with process integration? Can you guys follow process integration? Okay. I have a question. Why we have different layer of metal? Yes, exactly. Let's go back to metal. The role is different, and this is not generic for all devices, and it may not be even generic for CMOS. So different designs and different architectures may need different layers. Hold on. Let me go to metal one. Okay, I'm going back to the slide. So for example, for this particular case, you have 4 different metal layers for different purposes as your metal 1, and in fact metal 2, metal 3, and in fact it may be slightly different from metal 1 to metal 2, 2 to 3, 3 to 4. Okay, so for example, if we talk about this particular case, it may not be generic. I repeat. So you have anti-reflective coating for your tinitride, 50 nanometer, aluminum copper as your main conductor, 500 nano, tinitride again as diffusion barrier. Then you have titanium as electromigration shunt, an issue that we're going to discuss in metal interconnection and contacts, electromigration. So it's going to prevent shunting in the device. So it serves different purposes. Okay, so maybe we can search later on any difference in terms of metal 1 and metal 2, any different compositions that are available or chosen by a wafer fab to do deposition for metal 1, metal 2, metal 3, right? As far as I know, it's not generic. It's not generic for all cases, okay? Okay, Shah, tungsten plug and tungsten VR plug, same purpose, different tungsten VR plug. Okay. Okay, tungsten, are you referring to any specific page or general? If you're talking about general plug, so it's actually similar. So I should book out VR punya page. Where is it already? Okay. Tinitride, tungsten, hold on, plugs. Okay, CMP, the remaining tungsten form plugs, plug or general plug. Okay, right. So what you have in the VR, is called plug. So that is made of tungsten, deposited tungsten. To be able to get your tungsten plug in the hole or in the VR, you need to prepare the VR first. So if you're referring to the tungsten in the hole, then it's called tungsten plug, right, in the VR. So maybe it's mentioned together because it sits in the VR. So is there any page that I mentioned VR tungsten VR plug? Because the material is tungsten, but it sits in the VR, so that's why we call it tungsten VR plug. Tungsten plug, tungsten plug. Hold on, let me see. Tungsten VR plug. Okay, actually it's the same, okay? Same thing. Tungsten material sits in the VR. So VR is the hole, then you deposit tungsten, you CMP the tungsten, then you get the contact between metal 1 to metal 2, that's all. Okay? Right, any other questions on integration? So if you do integration, say if you do integration for wafer fab, so this is pretty much stuff that you have to do, but tapi ni saya example ni example yang simple lah. Example 2 metal je is actually nothing. Kalau wafer fab tengok saya punya example ni, they will just laugh at this example. But the goal is this. The goal is to give you the fundamental, the role, the process, the specs pretty much. Cumanya how many layers that you want to have is entirely up to the company. It depends on the device design, so the performance of the chip that you're looking at. So that brings the complexity into the equation. Tapi as long as you understand the different role of the different layers, the method to deposit, the method to grow, then you just have to repeat the very same thing for your metal 3, 4, 5, 6, with maybe slightly different specifications. But the fundamentals remain the same. Okay, so that's why saya letak kat sini, second to nth, as many as 8, for example, interconnect layers, right? So it's really customized depending on the needs or on the performance of the device each wafer fab is looking after, right? On the other hand, if you are, nanti saya akan cover dalam solar cell, if you are a process integration engineer, so kita ada seorang student apply, I think last year she went to She went to internship at Jinko. Now she's an R&D engineer or merangkap process integration engineer in silicon solar cell. So she's gonna handle, or he's gonna handle, process flow for the silicon solar cell fabrication. So then you're looking at different device architecture. You're looking at, for example, a wafer P-type, then diffuse N-type phosphorus, and then you're gonna have like anti-reflection coating. You're gonna have laser scribing for PERC structure, passivated emitter rear cell contact device architecture, and then you're gonna have your top contact silver. You're gonna have your rear contact silicon, then done. So that is the whole process integration coverage. For example, if you talk about silicon solar cell company. So the integration vary. You device. If you talk about cadmium telluride solar cell, for example, then you're gonna be overseeing process flow of ITO deposition, Cad sulfide as the buffer layer, Cad telluride as the absorber layer, and then you're gonna have like a couple of metal layers at the back as the rear contact, and then the probing, the interconnect between your device to device on the glass. So the role of the integration varies from companies to companies and product to products. In fact, device to device within the same company as well, right? The general role of an integration guy is to oversee the whole process flow. Either you're looking at the whole flow or specifically front end or back end or different devices. But to know the details of every process, you still have to go to the specific process engineers to be able to know the details parameters of that particular process. For example, a process integration engineer that's in charge for lithography may not know what's a DOF value for certain layers in lithography process. Okay, Naim, let's say for 5 nanometer chip, is the 5 nanometer referring to the distance between the metal? No, it's referring to the gate width of the polysilicon. But even then, you have some definition as well. Nanti kita akan ada fabrication for you're going to have presentation, right, for FinFET. I think one of the groups is are going to do FinFET. So we'll see how do they explain technology node as far as FinFET is concerned, and maybe we can discuss on the comparison for the CMOS, the dimension of technology node in the presentation. Okay, but generally it's referring to the gate width of the device. Tapi kalau you baca betul-betul, there are still few definitions of the gate width. In fact, there are few definitions of the technology nodes of CMOS, right? So it's not the distance between metals. So if you're talking about a vertical metal, Naim, or is it adjacent metal or vertical metal? Metal 1 to metal 2 or adjacent metal 1? Side by side metal 1 or metal 1 to 2? Because it's not the vertical one, of course, because that's not the 5 nanometer definition. That's not even the distance between your adjacent metals, but it's rather the polysilicon dimension. For example, if you want to know the device size, you have to go back to the front end. You have to go to your polysilicon definition. Saya buka polysilicon. Okay, gate. Right. So yeah, this is where you spin the resist, you pattern the resist to define the polysilicon gate. Then in the next step, right, this is where you define the gate. So generally, you can say that the size of the device is dependent or is determined by the polysilicon width. Cuma when it comes to the definition of technology node, we have a couple of definitions around this. Tapi it's not on the metal, it's on the polysilicon layer, right? Because that forms the gate on the device. So remember, when you talk about the transistor, you have to go back to the gate, source, drain. And in this particular case, you already have your gate on, made of polysilicon, and that's where you define the size. We'll see in the presentation later on. So I hope the group who's doing the transistor, please also include the definition of technology node on your presentation. Okay, what does it mean by technology node? So if you encounter a couple of definitions about the technology node, so please include the definitions in the technology node as well, in the slide as well. Okay. Okay. Any other question on the integration? Ada lagi ya? Now 10:37. Hold on, let me see whether interconnects. Tak ada. If not, then I'll just continue with interconnect for maybe another 15 minutes. Right, can you see the interconnection slides? All right, that's good. Interconnection and contact is the final topic of our class, right? Final topic of our course. I think we can finish either today or Thursday, right? Today or Thursday. So let's go through. So let's recall a few things on process integration. What are the 5 important modules in CMOS process integration? So what are the modules that we've learned? Anyone can write down there? Isolations, yes, good. What else? Lagi? Wells, good. Lagi? 2, 3 more. Junction, gate, stack, interconnect, right? Junction, gate, stack, interconnect. Ada lagi ya? Ada kan? So name and role for each color-coded region. You try to practice yourself, just like what I told you in the last few minutes. Okay. So interconnects and contacts concern with the backend, the interconnection, metal 1 until your final metal stack. So we're going to look at few technical things around interconnects and contacts. So metal contacts, when you work with metals, the fundamental of metal properties is in the resistivity of metals. So to be able to use the metals, you need to choose the right one. So that is one of the primary parameters that you have to consider when choosing the metals is the bulk resistivity of the metals, typically in the micro ohm cm. So if you can compare with silicon last time, we've been talking about 1 ohm cm, 0.1 ohm cm, 10 ohm cm, but this one is like 3 orders of magnitude lower in terms of the resistivity. So we're talking about micro ohm instead of milli ohm. So that's 1,000 times lower, right? If you talk about silver, for example, the bulk resistivity is usually around 1.6 micro ohm cm, aluminum 2.6, and you can see the range there, range of different materials with different bulk resistivities. Okay, commonly used metals are aluminum, titanium, tungsten, copper. You have seen the usage of some of these metals in the plug. For example, we have used tungsten plug to connect the metal, and in the metal layer itself we use titanium, tinitride, aluminum, copper, right, for different purposes. So these are the commonly used metal for the fabrication of IC. If you talk about silicon solar cell fabrication, then it's usually silver on the front side of the solar cell, aluminum on the rear side of the solar cell. The latest condition, the industry is moving into nickel and copper as well by electroplating in order to reduce the cost and improve the aspect ratio of the metal contacts to reduce shading into the device. We're going to see later on solar cell. Okay, types of contacts. We have various types of contacts. So you can see The first one is aluminium to p-type silicon forming ohmic contact, right? Ohmic contact, aluminium to silicon. So you have a pattern SiO2 in between, and then you open an area for the aluminium to access the silicon, either P or P plus. Okay. So aluminium is a p-type dopant as well, right? So aluminium to n-type, the one in the B, and in the middle one, can form a rectifying contact. So we learned last time about ohmic and Schottky. Okay, ohmic and Schottky contact when we learned about heterojunction in ZAT487. So we have learned about the difference between ohmic and the Schottky, right? So the issues and the drawing, the Fermi level and stuff like that, extraction of the carriers. C is aluminium to N plus silicon yield a contact, right? A similar contact to figure 7.3c. So aluminium sitting on N plus, but the N plus is sitting on N layer. So when last time I told you that when you talk about doping, you can encounter a range of different doping configurations. So it can be P on P plus, it can be N on N plus, it can be just P, it can be localized P plus on P, it can be localized N plus on N. Well, it can be different configurations depending on the device. For example, if you talk about this particular case, 7.3c, then we're talking about N plus sitting on N. We normally see this in solar cell. We're going to see later on why do you need to have this. One of the main purposes is to improve the contact resistance. So you want to reduce the resistance. So improving resistance here means reducing contact resistance between aluminium and your silicon. So if you just have a blanket doping, for example, N layer, you're not going to get easy formation of ohmic contact if you compare to N plus sitting on N, for example. So it's a lot easier for you to get your ohmic contact. Okay, do you have any idea why is it so? If you compare N versus N plus on N, why do you think it's a lot easier to form ohmic contact? Can you recall 386? If you dope the contact or the interface more heavily, then what's going to happen? Nanti you recall, huh? Try to recall. It has something to do with the barrier height. Okay, so on the right hand side, you can see IV curve. You can tell whether your contact is ohmic or Schottky, right? So you have, if you have your IV is like the first one, you can test it. You can test this on Hall effect. If you have a straight line, then it's going to be ohmic. If you have a curved line, it's going to be Schottky. Okay. Aluminium spiking and junction penetration. Okay, silicon absorption into aluminium results in aluminium spikes. So aluminium can be absorbed into, silicon can be absorbed into aluminium at the interface, which could cause aluminium spiking, right? So you can see the spike here. So you have aluminium contacts on the front side. You have pattern SiO2 on the front side as well. Then you have aluminium as your substrate. So you may have aluminium spike in the silicon instead of a clean interface. So that's due to the aluminium spike. Particularly if you subject the sample to annealing, right? So you can induce spikes more easily. Spikes can short junctions and can cause excess leakage. So barrier metal deposited prior to metallization, to be able to reduce the spike, you can deposit a very thin barrier metal. That's what you can see on this slide to reduce the occurrence of the spike. Right, barrier metal deposited prior to metallization, sputter deposition of aluminium with 1% of silicon can also reduce the frequency of the spike. Right, alloying of contacts. When you say alloy, then you are combining aluminum and silicon at the interface, for example, right, to obtain very low contact resistivity. So this is one of the reasons we heavily dope a small region under the contact in order to form a better contact formation, right? Better contact formation. You can see on this graph, if you anneal the contact, the aluminum silicon contact at a higher temperature, you can effectively reduce the contact resistance in terms of ohm per ohm cm squared, right? So you can see various combination here: aluminum N plus silicon, this one, silicon aluminum, silicon dope aluminum N plus, and then aluminum undoped polysilicon. So it's different configuration here, right? I'm just going to stop here. We're going to continue with electromigration on Thursday. Okay, so we're going to see what is actually electromigration on Thursday. Okay. Okay, so I'll see you again Thursday. Do you have any questions on your presentation? Ada apa yang nak tanya on presentation? Before you plan, sit down together. No? All good? I plan to have your test 2, okay, test 2, will be on the final week. So now it's 13, 14, 15. So yeah, I plan to conduct your test 2 on 19th of January. 19th of January, Tuesday, during our Tuesday class. So 19th January, Tuesday, 9 a.m. Okay. So do you find, okay, you tell me now, do you find your test 1 duration 24 hours too long? Any feedbacks? No haha, right? No haha, okay. No haha means too long, right? Just fine? Really? Anyone think it's too long? Anyone think it's too generous? Just fine, Azika? Macam gelap besar tu. No, Shah, no. Okay. Please add down here. Let me see your majority feedbacks. No haha is a good answer. Just fine. Good smile there. It's okay for you, all right? No. So it's okay? 24 hours is not too long. Okay, good. So would you like it to be 12 hours instead? All right. That's long, Jenny. No, Amira, no. Big no, big no, right? No smile now. Okay. So 24 hours, much better. It's too much, huh? And Naim, is it too much? Too much better? Yeah, okay. Big no for 12 hours. I was thinking this morning of 12 hours, to be frank. Yeah? Big no? All right. So let's see what do you have for your test 2. Test 2 is going to be on... Oh, another test. If that's the case... Oh, you too? Open book as well? What if... Hold on, let me see the calendar now. So how about Monday? Monday 18, day before. Oh, ya ada test juga 18. Uh, we're gonna finish our classes by then. So how about Wednesday? Tak ada kelas lah, tapi it's just a test anyway. How about Wednesday? Please tell me Wednesday. No comments means okay. Is it okay? Wednesday, 20th of January. Rabu. Okay, so I assume yang mana tak cakap apa-apa, okay ah. So if you're not okay, tell me not okay. If not, then I assume it's okay. So yeah, so it's gonna be on the 20th then. 20th Wednesday, 9 a.m. 20th, all right then. So we're gonna finish electromigration on Thursday. Then this Friday, I'm gonna give you a special lecture on silicon solar cell fabrication. At least you have some ideas of some other device fabrication. So you have learned about fabrication of LED from OSFAM, and for some other devices, you can just explore yourself, right? If you want to join SSD, for example, or power devices, IGBT, or silicon photonics, or biosensors. So you may want to explore yourself as well, because if you go for if you interview for Sotera, for example, so the content may range from CMOS, it may go to silicon photonics, it may range to biosensors, because they are now doing different devices for the fabrication. Okay. So that's all for today. I'll see you again Thursday. We'll continue with electromigration. Okay. Bye bye. Take care. Assalamualaikum.